Hello AP, this is Mrs. Sargent, and this is section 12.5 in your book. We're going to talk about reaction mechanisms. So reaction mechanisms are a diagram or a series of steps in which the chemical reaction occurs. So sometimes with more complex chemical reactions, the reactions will occur in more than one step. An intermediate is a species that is neither a product nor a reactant in the overall equation. It is used up in a subsequent step. So you don't see it at the beginning of the reaction, you don't see it at the end, but in the in-between, you have this species or compound that is formed. An elementary step is a reaction whose rate law can be written from its molecularity. So molecularity is just going to be referring to the coefficients in a balanced equation. A little bit more about molecularity. It's the number of species that must collide to produce the reaction represented by the elementary step. So here is a reaction mechanism, and we're going to label some different parts on this diagram. So to start with, we can see that there are two distinct hills or humps, whatever you want to call them. The yellow here, this is for step 1, and then the let's try to do red. This is going to be for step 2. Okay, so we're going to label some different things on this diagram. To start out with, here in step 1, you can see the activation energy is labeled. So this is the starting energy of your reactants, and in order for this step to occur, we need this much energy. So activation energy, this is sometimes labeled EA1 because it's for the first step. And so one thing that we can tell from step 1 is that the reactants are going to become intermediates. And the reason why I know that is because my reactants that are given in this reaction are the hydrogen and the ICl, so my overall reaction is H2 plus 2 ICl, and then my products down here, I have I2 and 2 HCl. So here, after step 1 finishes, I have an intermediate that forms, and that intermediate is the HI. So reactants become intermediates. This is also going to be a slow step. We'll talk more about what it means to be a slow step in a little bit. But in order for this reaction, this first step to occur, we need more energy than what the reactants have. So it needs more energy. Then for step number 2, we have step number 2 over here. The reactants and the intermediates become the products. And so when we look here at the beginning of step 2, we have some of the reactants, and then we also have intermediates that form the products. And step number 2 is going to be a fast step. It requires less energy than what the reactants started with. So that's one of the reasons why this is going to be a fast step. So we're going to look some more at reaction mechanisms. There are different types of reaction mechanisms. A unimolecular step, a reaction step involving only one molecule. So if you think about like unicycle only has one wheel, unimolecular step only has one molecule. This is pretty common for reaction mechanisms, that there is only one step. A bimolecular step, a reaction involving the collision of two molecules. So like a bicycle has two wheels, two molecules here for bimolecular. And the rate law is always second order. And then termolecular, a reaction step involving the collision of three molecules. So bimolecular is a little more rare. And then termolecular is very rare. So starting with our most common, going to our most rare for reaction mechanisms. The rate determining step is the slowest step of the reaction. So if you think about, if you're walking with a younger brother or sister or niece or nephew, and they just can't walk as fast as you, they're going to determine how fast you walk down the road. The slower person determines the rate. And then activation energy. This is the starting energy. To the highest point for that step. So the height of the step determines if it is a slow or a fast step. So you can see the slower step has a higher point, and that is the slow step. The fast step has a lower point, and that goes faster. So an elementary reaction agrees with the balanced equation. Their reaction mechanisms must add up to the balanced equation and agree with the rate law. The thing is that we can't prove a mechanism absolutely. We can only come up with a possible mechanism. So here we have the elementary reaction, NO plus N2O yields NO2 plus N2. So for this reaction, when we go to write the rate law, we are going to say rate is equal to our rate constant times the concentration of NO times the concentration of N2O. Both of these are have 1 for the exponent because we only have one of those in our elementary reaction. So the elementary reaction is going to be written just like we talked about rate laws in section 12.4, determining the rate laws. So this next reaction is a little bit more complex. It says 2NO2 plus F2 yields 2NO2F, and it is thought to proceed via the following two-step mechanism. So we have NO2 plus F2 yields NO2F plus F, that is your slow step, and F plus NO2 yields NO2F. So we're going to write the rate law based off of the slow step. So NO2 times F2. So if your first step of the reaction is the slow step, then you're going to write the rate law off of that. Ignore the fast step if it occurs second. The first step, the slow step, dictates how quickly the reaction can occur. So we'll pick back up here with some more complex rate laws and reaction mechanisms.